Okay, good morning, all. So let us just recall what we have discussed in the last class. So we have seen a couple of examples that can be solved as a linear system of equations, and we can use this matrix algebra to find out the solutions to those electric circuit problem or chemical bonding, chemical reaction problem, or other rocket launching problem. All those things we have seen. And there is a beautiful application of Gauss Jordan method. Gauss Jordan application, the Gauss Jordan elimination, helps us to find out RREF. Okay, now if let me just tell you this solutions later. First, let us recall the cases of solution of a system of linear equations. There we have seen either we can have a unique solution, or we may have infinite number of solution, or we may have a situation where there is no solution. So these three cases we have observed. But remember, the right hand side was a non-zero vector. Okay, so the right hand side was a non-zero vector. Now what we want, if we have the right hand side is zero vector, that means a homogeneous system. So homogeneous system is always consistent. Either it will have a unique solution when the order of the matrix and the rank will be equal. Okay, and if the order of the matrix and the rank of the matrix are different, order is n, but the rank is less. So then in that case, we will have infinite number of solutions. So consistent system will have two cases, either unique or many, when we have the right hand side as zero vector. Now there is a beautiful application of this finding the inverse. This Gauss Jordan method. So just to recall, easy to remember, this theorem will tell the existence of unique solution and the no solution case. Okay, so yes, linear system is said to be consistent if and only if. Okay, it is another way of representing if and only if it has at least one solution. So when it will have one solution, when we have a feasible case, that means, for example, if we have that, this case. If you remember that case, this is the RREF. RREF reduced row echelon form, and the last row what we have, it is having 0, 0, and this is non-zero. So this is non-zero entry. So the theorem says if we have a non-zero row at the of this form, okay, the rightmost column in the augmented matrix, okay, the rightmost column of in the augmented matrix. So this is augmented matrix, the rightmost. So this is the rightmost column. If we have of this case, so 0, 0, B, which is non-zero, okay, so if we have a kind of this kind of zero row, sorry, non-zero row in the augmented matrix, then what happens? So 0 x1 plus 0 x2 plus 0 xn becomes 0. B is non-zero. So 0 equals to some kind of non-zero entry. So which will be inconsistent. Okay. So this theorem says if we do not have such situation, then we will have a consistent system. That means at least one solution will be there. Now, if a system is consistent, then we will have either unique solution or infinitely many solution. Now, this unique solution will have when there is no free variables. We have defined what is free variable and what is basic variable in the last class. Okay, and infinitely many solution, if there is at least one free variable, then we will have infinitely many solutions. Okay, so this theorem is very important. So whatever the case that we have discussed so far is actually summarized within this theorem. Now, in order to, for example, if you want to understand the application of a matrix, you want to send one message to me, to some other. So what you need just this email ID. This can be subject. So you will see how this message can be, how we can find the application of matrix inverse in the sending some message. You also want to know that the message should be secure. It should not go somewhere else. So somebody knows that. So that kind of applications, it's like cryptography applications can be seen. So what you do is actually you send some numbers, arbitrary numbers for 19. Okay, then maybe 5, then maybe 3. Then you can say, for example, 18. Then you can write 20. Maybe this will give AC, C, R, okay, ACC, PR, ET, maybe secret. E again is 5. Then 20. Secret. Maybe this is for C, you can write. If you want to generate some code, secret, some message, this is a secret code. For the message is secret code. C is 3, 0. And if you want to put a blank, so you can write here 0. So 0 will give one space. One space will be there. So this is 3. See, O is 15. Then D is 4. E is 5. So if you want to send a message to me or some your friend or someone, you just send these numbers, okay? And then tell that assign 1 to A, 2 to B, 3 to C, and find the message. It's like playing a game, finding the secret message. It is like the game that you play in treasure hunt or some other things. So you can find the applications of inverse here. Now, if we have this kind of secret code, so this is secret, one space, that is 0, there is a blank space, and then another message. There is code, one other word. So for this, what we need actually one matrix, a 2 by 2 matrix. Since we have two words, okay? So we need a 2 by 2 matrix for which, like if you want to send a message to me, you will need this one. So this is similar to the 2 by 2 matrix. So this is, you can say, this is a 2 by 2 matrix. So this is given, and you are trying to send me this message. Okay, this can be treated as the email ID. This will be given. You see, if you want to send a message to me, you don't need my password. You just need the email ID. So this would be publicly given. Okay, this would be publicly given. This is also given in publicly. Sometimes when the message is coded. So this message we have to read in this way. We will follow this column wise. Okay, here to here, and then here to here, and then here to here, up to this. And not a row wise, we will see the message in the column wise. Whenever there is a 0, so there is a blank space, and then we'll again start from here and then here. So this is another blank. If suppose some more values are there, then again we have to start from here and this way. We have to study this code. Okay. Now what we do, we just multiply the matrix A matrix and thus B matrix. B is the encoded matrix and A will be given. So if you just multiply them, then you get the coded matrix is this one. Okay. So you send this to this message. Even in WhatsApp also they use some encoding, one-to-one encoding, this kind of situations. They use matrix theory also. Now in order to find this message, that secret message, you will send this message to your friend and he or she will get the actual message in this way. The number will be there. So how this is done? So in this case, matrix theory is very, very useful. Okay. So for that we need to understand how do we get the inverse. We all know how to find the inverse of this matrix. Since this is a 3 by 3 matrix, so our task will be easy. But if it is 100 by 100 or 1000, okay, or the order is 4 times, or maybe some larger, then how to find the inverse? Okay, so the hand calculation definitely is not going to help us. So for that, again, we need to understand the some different methods which is more suitable for higher order matrices. Okay. Now this is the message you send to your friend. You want to tell, use this as the key. Okay. So that whatever you get after multiplication, okay, that will be your message. So after multiplication, finding the inverse, take the inverse, A inverse, and then multiply the C matrix. C is this matrix, and A inverse is this is given. You tell your friend that whatever I am giving this matrix, you just take the inverse and multiply with the message. And this message will be arranged in this way. Okay, in this way it will be arranged. So you have to get it. So now you get this message. Message is this 23,855. Since there is a 0, so there will be a blank. So for this, W is associated to 23, and 8 means you are assigning the value age to 8. So this becomes who. Then another message, that is another blank. So blank is there. So here, who is Carl, and then Gauss. Okay. So you send this message, and this message is encoded as who is Carl Gauss. In fact, those who from the beginning you know that Gauss elimination, he was a great mathematician, has done so many works in Gauss Jordan. The method that we could find the Gauss Jordan, this who is Gauss, you can find in Wikipedia or Google if you search who is a Gauss. Now, as you can see that the application of inverse is very important in several applications, several fields of engineering and other computer science also. So you can see that. So it remains to find how to find A inverse for a given A n by n matrix where n is greater or equals to 4. 3 by 3 we know that we have to find the A inverse is the formula. So this formula will be applicable for all, taking the adjoint of A and then we take the determinant of A, provided the determinant is non-zero. Okay. But if we have 4 by 4 matrix, then it is difficult to calculate the adjoint and then other determinant. Okay. But there are some method. This particular method has one beautiful application. This Gauss Jordan elimination that we have done in our so far that we have seen in the previous lectures. So it can help also to find out the inversions. Now what it happens, similar to the augmented matrix, we'll put on a line, okay, and the given matrix, this will be given. Equating to this order, what we'll do, we will take another same order matrix, identity matrix, and we'll do the row operations, either E1, E2, or E3 that we have seen in the row operations. After row operations, we will try to find out the identity matrix on the left hand side, and it is guaranteed that whatever we get on the right hand side, that will be inverse of the matrix given here. Okay. Now the same thing can be done if you think about the augmented matrix. For example, the matrix A, it is given. Okay. So what we do, we try to find out, if you do this 0, for example, A, and then you take this only one column, 1, 0, 0, 0. Okay. And you try to find out the matrix, whatever you get. So, yeah, the left hand side, it will get I, and then you will get some values. Okay. Similarly, you can take the second column and repeat this process, take the third column, repeat this process, and fourth column, and repeat this process. So these values will be, you can count it. Okay, you just write the values. If you do separately, taking each column at a time, okay, then whatever you get, and the other process, if you take all the columns at a time and repeat the row operation, then also you will get the same values. I will show how to get these matrices. So first, let me just tell you. Yeah. So this example is, yeah, A is given. Our target is to, aim is to find out given A, we'll write AI. Okay, row operations. And then we'll try to find out I just A inverse. So let us write the matrix. What is given? Matrix is given 0, 2, 1, 3. Then 1, 1, minus 1, minus 2. Then 1, 2, 0, 1. Then minus 1, 1, 2, 6. Since this is a 4 by 4 matrix, so we have to include one a identity matrix of order 4, 1, 0, 0, 0. So 0, 1, 0, 0. Then 0, 0, 1, 0, and then 0, 0, 0, 1. So that's what we have. So we want to, yeah, our aim is to get it in this form. Whatever we do, there should be, these values we don't bother about it. Whatever we will get will be, that will be our inverse. Okay. But what we want is, we want identity matrix in this form. 0 1, sorry, 0 0 1 0 0 0 0 1. Now how do we proceed? So first task is to, so this will be our final destination. Okay, start. Now let us understand the intermediate steps. Okay, so initially it is 0 here. So what we want 1 here. Either we can put it here or we can put it here. So let us take the R2. So this row 1 is exchanged with row 2. I mean, this process is very simple, just a lengthy process. Okay. So if you just shift it, so it will become 1, 1, minus 1, minus 2, then 0, 1. Similarly, we have to shift this also, okay? 0, 0. And row 1 becomes, row 2 becomes now 0, 2, 1, 3, 1, 0, 0, 0. And we write other rows as usual. 1, 2, 0, 1, 0, 0, 1, 0. Then minus 1, 1, 2, 6, then 0, 0, 0, 1. Okay. Next, what we want? We want 0 here. And also we want 0 here. So for that, what we have to do is, okay. Okay, so what we have to do is row 3 minus whenever we are trying to make something 0, so we'll take the help of the pivot element. Remember, here it is pivot. First non-zero leading entry. Leading non-zero number, or we call it a pivot. Actually, we take the help of pivot. Okay, whatever you call it. So this is called pivot element. This is pivot row, and this is pivot column. Okay. So here we will take the help of this pivot element to make them 0. So how do we do that? This is R3 minus R1 and R4 plus R1. So let us write down. So R3 minus R1 and R4 minus, sorry, not minus, it should be plus R1. So this becomes, so let us write down the first row is 1, then again 1, minus 2. So this is 0, 1, 0, 0. We are not doing with the R2. R2 is 0 here. It is our task is reduced now. Okay. Then it becomes 2, then 1, then 3, then 1, 0, 0, 0. And then since R3 minus R1 we are doing, so it becomes 0 now. Okay. And then R3 minus R2, so 2 minus 1. So this becomes 1. Similarly, 0 minus of minus 1. So it becomes 1. Okay, 1. And similarly, repeat the process. It becomes 3. So 0, minus 1, 1, 0. And then the fourth becomes fourth row becomes, we have to add R4 plus R1. So this is minus 1 plus 1. So this becomes 0. Okay. So let us put here 0. Then R4 plus R1, it will give here 2. And then again it will give us 1 and 4. Finally, on the right hand side, we will have 0, 1, 0, 1. Now, what we want? We want 1 here. And we want 0 also here, 0 also here. Because the this left hand side matrix, it should be identity matrix. So we'll do one by one. So now the pivot element is this one. So what we have to do is, we have to, okay, one thing we can do, either we divide this row, it will be 1, then it will be half, and then it will be half. Either we can do it, or
R2 minus R3 you can do.
we can exchange. We want to exchange R2 exchange with R3. So if you do that, then this becomes 1, 1, minus 1, minus 2. Okay. 0, 1, 0, 0. Now it will go here. So 0, 1, 1, then 3. Then 0, minus 1, then 1, 0. And this is becoming here, coming down to here. So this becomes 0, 2, then 1, this is 3, and 1, 0, 0, 0. And then 0, 2, 1, 4, 0, 1, 0, 1. Okay. The next task is to get these two as 0. Okay. This one and this one. We have to make 0. So this is our pivot element now. Okay. So 1 is our pivot. So what we do is R3 minus 2 times R2. This is R2 now. Okay. And R4 minus 2 times R2. So this will give us another matrix which we want to write is as, so first row is as it is same, 1 minus 1 minus 2, 0 1 0 0, then 0 1 1 3, 0 minus 1 1 0, and then we want to make 0 here, it will be 0. So 2 minus 2 times 1 0, so 1 minus 2 times 1, so this becomes minus 1. Okay, and then this becomes minus 3. Here it is 1 2 minus 2 and then 0. Similarly, it becomes 0 0, this is minus 1, then this is minus 2, and this is 0 3 minus 2 1. Now we want 1 here. So what we can do, if we exchange, nothing will happen. So what we do, we multiply with minus 1. Okay. So the next task is to, so minus 1 times R3. It becomes, okay. So it is becoming now 1 1 minus 1 minus 2, 0 1 0 0. Then it is 0 1 1 3, 0 minus 1 1 0. Similarly, we have 0 0 1 3, minus 1 minus 2 2 0, then 0 0 minus 1 minus 2, 0, 3, minus 2, 1. So that's what we have so far. Next task is to make this one as 0. So this is our pivot element now. We want 0 here. Okay, so let us do that. R4 plus R3. This will give us the desired 0 in that place. So 1, 1, minus 1, minus 2, 0, 1, 1, 3, 0, 0, 1, 3, 0, 0, 0. So we are adding, so this is 3 plus minus 2, that becomes 1. Okay, the right hand side I forgot to write. So here also, okay, we have to do first row is complete. We have to do the first row is complete. So this is 1, 0, 0, then 0, minus 1, 1, 0. The third row, this minus 1, minus 2, 2, 0. And then it becomes minus 1, 1, 0, 1. Okay. Now that we have done, all these ones are here. So main diagonal, it is having 0. So the next task is to make all are 0. Now this is our pivot and we have to make this one as 0. Okay, this column is 0. Okay, so for that we have to do those operations. So if you do R1 plus 2 times R4, R2 minus 3 times R4, then R3 minus 3 times R4. If you do this, you will get 1, 1, minus 1, 0. Then it is 0, no, not 0, it will be now minus 2. Then this is 3. Since you are multiplying, okay, this is 1 into 2. So minus 2. 0 plus minus 2. So this becomes minus 2. Now 2 into 1, that is 2, plus 1. So this becomes 3. Similarly, 0 plus 2 into 0. So this becomes 0. 0 plus 2 into 1. So this becomes 2. Similarly, for the other rows, 0, 1, minus 3 times R4. So this becomes, okay, this is 1. This becomes 0. Now this is becoming 3 minus 4, 1 minus 3. Similarly, it will become 0, 0, 1, 0. And the right hand side will become 2, 5, 2, 2 minus 5, 2 minus 3. And the last row 0, 0, 0, 1. It becomes minus 1, 1, and then 0, 1. Next, what we do? We want zeros here also. Okay, now only 3 quantity is remaining to make them 0. So let us do this column now. So here it is. What we can do is now we have to do R1 plus R3 and R2 minus R3. Remember, for each operations, we have to understand which one is the pivot. Now here it is the pivot and we want to make them 0. So this will be our multiplier to make others 0. Okay, so that is why we want these operations. So for this reason, we'll have 1, 1, 0, 0, and then 0, it becomes minus 2, 2, and minus 1. Then it becomes 0, 1, 0, 0, then 1, 1, minus 1, 0. Similarly, the third row will become as it is 0, 0, 1, 0. So 2 minus 5, 2, 3, minus 3. The fourth row 0, 0, 0, 1, minus 1, 1, 0, 1. Finally, we want 0 here, and this is our pivot now. So what we do? We do this one, R1 minus R2. So what we have now is this matrix 1, 0, 0, 0. And this one will become minus 1, minus 1, minus 3, 3 minus 1, 0, 1, 0, 0. It becomes 1, 1, minus 1, 0. And then what we want is, sorry, this is 0, 0, 1, 0. It will become 2 minus 5. Then it is 2 minus 3. 0, 0, 0, 1. Becomes 0, not 0. This is minus 1. And then 1, 0, 1. So this is our, we have our A inverse for the given matrix. This is our I4. Okay. That's a lengthy process, but not a difficult one. You just have to be patient to get all the steps done. So this is our given matrix A, and we have found the A inverse. And we have used the Gauss Jordan elimination. Now, if you go back and check for each, if this matrix is given to you, if a higher order matrix is given instead of 3 by 3, if some more higher order matrix is given, and the message length is more than that, then also you can find out the message that is encoded within the matrix. So you can find out what is given in the matrix. So this is how we use the Gauss Jordan elimination to find out the inverse of a matrix. So use Gauss Jordan method. I know this is a 3 by 3 matrix, and you can always use the method of A inverse equals to adjoint of A by determinant A. Okay, don't use this one. Use Gauss Jordan elimination to find the inverses of the given matrix. Verify whether these results are correct or not. If you find any discrepancies, just inform me. I'll do the changes accordingly. Okay. So after this, we have found out that how we can use the Gauss Jordan elimination to find the inverse of a matrix. Okay. Now there is another form which is very closely related to the Gauss-Jordan form. And these forms are called as normal forms. Sometimes some authors will call also canonical forms. So what are those forms that we have? Okay, these normal forms are actually used to find the rank of a matrix. If you want to find out the normal form, it is one of the four of this case. Case 1 is IR, or it can be of this form, or it can have also in this form, or it may have this form. So these are the four possible cases of a normal form of a matrix. Given a matrix A is a matrix is given. Okay. After row and or column operations. Why I am writing and or? Because in order to find out the normal forms, if we use only row operations, then it can take so much time. But if we use the column operations also, like we have done for the row operations, then it will help us to find out the normal form easily. So this will be formed as either one of them, IR type 0, 0, 0, or it can be just IR type. So whenever IR, that means 4 by 4 matrix, if the rank is, so this is our and row, the rank of a matrix is denoted by row of A is R, that is rank. So these are the most popular form of the canonical form of the normal form of a matrix. Given a matrix, find out the form. So if you just use the Gauss Jordan elimination, then you will get these forms. Okay. So this is I3, 0. This is I3, 0, 0, 0 of this form. So this is fourth type. This is third type. This is first type. I4. Okay. This is second type example. This is third type example, and this is fourth type example. Now you can see that the rank of the matrix is here. It is 4. Here the rank of the matrix is 3. Here also the rank of the matrix is 3. Also in this case the rank of the matrix is also 3. Only 3 rows are non-zero rows. If you consider it as a row echelon form. If you want to find out the reduced row echelon form, then automatically you will get this form in the middle of some of the step. So that is why if you use this RREF form, so that will be more sophisticated one to get some valuable information about the system of the linear equation. Okay, so that's what called normal forms. So you how to get the normal forms? Again, you have to use the concept of Gauss Jordan elimination to find out the normal forms. Now this is another definition, rank of a matrix. Okay, if you recall that rank of a matrix, so you can find it here. All the things are coming together here now. Rank of a matrix. Definition 1 says Definition 1 says number of independent rows. Definition 2 says number of non-zero rows in the row echelon form of A. Okay, that's what we have seen, two definitions. Now there is another definition which is very much equivalent to this. I mean, if you find, you can, if you try to look closely, then you can relate that it is nothing but whatever we have seen earlier case. The rank of a matrix, for example, if it is R, then it has at least one non-zero minor of order R. Okay, now if you go back and check, here it is, R is the rank of the matrix, assume. Then we will have one minor. If you take one minor of order R, then this becomes non-zero. Okay. What is the determinant of this minor? It is 1, which is non-zero. Similarly, for this one, it is the 1. But if you take the total minor, the 4 by 4 order minor, then it becomes 0. So the rank is not actually full rank. It is not having full rank, but it has the full rank as non-zero. Okay. So everything is actually connected here. So yeah, in this case, every minor of A of order higher than R will be 0. So if the rank is R, okay, if the rank is R, here rank is 3. If you take higher order minors, then it becomes, for this case, here the rank is 3. If you take minor of order 4, delta 4 as the minor of 4 by 4 order, then it will become 0. The determinant becomes 0. So minor becomes 0. Okay. So for the rank definition, we can also define that for a m by n, for a m by n matrix, take R is the maximum if rank of A is rank of A is equals to R, if then the minor of order R, delta R, is non-zero. Okay, more than that it will become 0. So this is another way of defining the rank of a matrix. Anyway, if you have understood these two definitions, then you are sufficient. These are extra, somewhere they are useful. But if I ask you to define the rank of a matrix, you can define either this one or this one. Now you have another definition, so you can call it a 3. Number 3 definition, number 3. Okay. So in the next class, we will see how to find the normal forms of a matrix. So before I conclude, like I asked you, if you have any doubt, you can ask me